Top 10 blockchains, top 10 consensus algorithms. Proof of stake, POS. The key idea behind this mechanism is for blocks to be validated by validators that have invested coins in the system. The more coins a validator has in escrow, the more chances he or she has to validate a block and earn rewards. This requires that coins are mined early enough so blocks can be validated from the launch. POS is a system where validators are not the creators of coins, so that transaction fees provide their only rewards. Blocks deemed valid and pushed by validators are always verified afterwards by the network. If a validator has tried to cheat, he loses all of his coins held in collateral. Example, Ethereum 2.0, Peercoin, Blackcoin, NXT. Delegated Proof of Stake, or DPoS, has an added delegation phase. During this phase, decentralized votes are made by the witnesses. Witnesses are users that are asked other users to transfer voting rights to them, thereby maximizing their chance of being elected validators. The witness group has the same function as the parliament in a parliamentary democracy. Another special committee group decides on the value of parameters such as fees, rewards, or how many witnesses compose the witness group. This committee does not receive any rewards, and these parameters can only change by vote during another maintenance phase. Liquid Proof of Stake. Tezos has developed LPOS, an evolution of DPoS, though delegation is optional. As opposed to DPoS, any user can become a validator if she has enough coins. If she doesn't, then she has the choice to delegate. The idea is to dilute even more the mining activity and to increase inclusion. In LPOS, a validator is called a baker. Any user owning enough coins can become a baker. Suppose a user wants to benefit from baking but doesn't own enough coins or doesn't have enough technical knowledge. In this case, they can delegate these coins to bakers, thereby benefiting from a portion of the transaction fees. The probability of winning a bake is proportional to the amount invested. The baking time is organized in cycles, and coins are locked during this time. Proof of burn, POB. Instead of investing computational power and electricity like POW, users in POB must burn some coins to gain a chance of becoming the next validator. Burning coins means sending them to a locked address where they are irretrievable, thereby destroying them. The more coins a miner burns, the more likely he is to validate a block and win rewards. This mimics the process of mining where miners have to invest some value, except instead of electricity, they use coins themselves. Examples, Slimcoin. Proof of Capacity, POC. This consensus first generates large datasets called plots. The more plots a miner records, the more lottery tickets they own. Hence, the more hard drive space, capacity, they have, the more chances of winning the rewards. This also mimics POW mining. Instead of accumulating cash power, you accumulate hard drive capacity. Variations, proof of storage, proof of space. Examples, Burstcoin, Storj, Filecoin, Bitcoin HD. Leader-based consensus LBC. Nodes elect a temporary leader node. This leader is then responsible for validating transactions and for ordering them. They are not necessarily made into blocks, i.e. having more than one transaction. Examples, BigChainDB. Practical Byzantine Fault Tolerance, PBFT. In this consensus, each node of the network awaits messages from the others. They are continually broadcasting messages. Each node receiving a message runs a program on it using its data. Each node results in then transformed into a new broadcasted message to all other nodes. With time, according to program rules, enough nodes will transmit the same result in the message. The total sum of these broadcast results determines the consensus. Examples, Evening chain. Federated Byzantine Agreement FBA. In this distributed network, sets of enough nodes to validate data are established. It means the sufficient number of nodes in a group is determined best. It means the sufficient number of nodes in a group is determined to best reach an agreement for that group. A single set of nodes is called a quorum. With FBA, a subset of quorum can aggregate another node, which in turn approves data to form a complete quorum. This subset is called quorum slice. Each node chooses its multiple quorum slices to trust. The aim of this is to avoid separated divergent quorums and to ensure that all quorums converge. Quorum slices must be large enough to have intersections or shared nodes. To summarise, validator groups with sufficient base size can aggregate single nodes from other groups. In the end, agreed quorums would cover the majority of the network, reaching a consensus. Examples: Stellar, Ripple, Avalanche. Each validator randomly selects n nodes among all the other validators. The more coins a validator has, the more chances it has to be selected. Each queried validator responds with its decision. If most responses differ from the asking node's decision, it will change its answer to that of other nodes. In case of disagreement between nodes, more nodes are brought into the decision, and more until convergence. Thus the name Avalanche, as it resembles this form of consensus. Examples: Avalanche. Proof of activity, POA. It is split into two ordered phases. POW phase. Miners race to find enough zeros in the result of a hashed function, but this time the block they validate is usually empty of transactions. Only the address to receive a reward and the hash and nonce is present. POS phase. A random group of validators is chosen to sign a new block. The more coins a validator owns, the more likely they are to be selected. When all the validators have signed, the block is filled with transactions. If there are not enough validators for a valid block signing, another valid block and another group of validators are chosen. Fees, rewards are then split between miners and validators. Example: Decred. Pros and cons. Proof of work, advantage, extreme robustness. Disadvantage, high energy consumption. Proof of burn, robustness similar to POW. Still disadvantage, still waste resources needlessly. Mining power to money burners. POC, proof of capacity. Advantages, less energy consumption, mimicked mining. Disadvantages, nothing to stake, tends to destroy hard drives. Leader-based consensus. Advantage, less energy consumption. Disadvantage, leader centralized cyber attack weakness. Practical, Byzantine fault tolerance. Advantage, very easy to implement. Disadvantage, absence of privacy, cyber attack weakness. Federated Byzantine agreement. Advantage, modest computing and financial requirements. Disadvantage, quorum slices centralization, cyber attack weakness. Avalanche advantage, fast, highly distributed, lots of nodes. Disadvantage, groups of nodes, centralization, cyber attack weakness. Proof of stake advantage, less energy consumption. Disadvantage, coin owners, centralization. Other problems: proof of activity. Advantage, more distribution on transaction selection and fees rewards. Disadvantage, combines POW and POS disadvantages. Delegated proof of stake advantage, less energy consumption, mitigating POS centralization. Disadvantage, coin owners and witnesses centralization. Liquid proof of stake advantage, less energy consumption, mitigating even more POS centralization. Disadvantage, still some coin owners centralization.